In this video, we take a look at some of the difficulties that can arise when we're looking at section 15.5 and triple integrals. Okay, so we're trying to integrate some function f over some region r, and the dv here indicates that we're doing a triple integral. You can see the three integrals, and from this notation we can imply that the function that we're integrating is some function of three variables x, y, z, and the region R has to be a region of three-dimensional space, 3D. Okay? And one thing that can happen in these problems when you're doing a triple integral is that there are 6 different ways to write the problem. Right? The first way is that you can do an integral of this function, f of x, y, z, whatever you're given, and the order can be dz, dx, dy, for example, in which case you would have your z limits, then your x limits, then your y limits. Or you could have a triple integral of a function, right? And then you integrate dz, dy, dx, in which case you are describing your region differently as z's description first, then describe it in terms of y, then finally, last, describe it in terms of x. Or there's a third way, right? And all these are just representations of the triple integral. They will all give the same answer if you set up the regions correctly, that you can integrate dx, dy, dz, for example, in which case you have to describe your x's first, then your y's, then your z's. Right? And then there are 3 other different interpretations, the dx, dz, dy, and then the ones where we put the y's first, dy, dx, dz, or dy, dz, dx. There are your 6 different ways to set up a triple integral. And keeping in mind, they should all give the same answer. All give the same answer if the limits of integration are set up correctly. If the limits of integration are set up correctly. Okay? So in this problem, you're being asked to write 6 different iterated triple integrals that represents the volume of the tetrahedron cut from the first octant by the given plane. And then they say to evaluate one of the integrals. Okay? So we are going to do 2 different ways, and then I'll leave you to set up the other 4. Okay? And let me just show, because I have a little bit of hindsight on this problem, let me first show how you can set up this problem just by using pure algebra. Okay? We're doing a volume integral, so therefore the function we're integrating is 1. Okay? One of the easiest integrals to set up, or the one that people think about the most often, is to do the z integral first, which means that z is going to be the first limits we need to set up, and the function can be a function of x and y. And z could be some other function of x and y. And it's up to us to figure out what these functions are going to be. Okay? Now, some sort of sketch would be helpful here. So the thing that's being asked about is that we're trying to find the volume of this tetrahedron, and not quite sure what that is, so let's, well, I know what it is, but if this is the first time maybe you're seeing it, so let's think about what that is. We have to be in the first octant, which means that x has to be bigger than 0, y has to be bigger than 0, so we're getting these major planes. This is the plane x equals 0, this is the plane y equals 0, And then there's another plane in the bottom, z equals 0. Okay, there are some planes. And we're trying to find this plane. This plane comes into this region where x is bigger than 0, y is bigger than 0, and z is bigger than 0. There's a part of the plane that comes through here. Okay, this part of the plane cuts into this region to create the part of the plane in that region, and we're being asked to find the volume, okay, that is below this particular triangle but trapped between all those three different planes. So the thing to see here is that z is going from 0, the plane z equal to 0, up to the equation of the plane. That means that z is going to go from 0 up to solve this plane, 6x plus 3y plus 2z equal to 6. Solve for z to get 3 minus 3x minus 3 halves y. So that's what you would put here for the top, 3 minus 3x minus 3 halves y. Okay. And now you get to move to, okay, stop thinking about a 3D picture. Okay, you're done with that because now you can think about what happens in the xy plane, which was what happens when z is equal to 0. This plane cuts through, okay, the first octant, and when it cuts through, you get want to see what happens when that plane crosses the xy axis. So when z is equal to 0, you get 6x plus 3y equal to 6, which then tells you that 3y equals 6 minus 6x, or y is equal to 2 minus x. Which means that in the xy plane, the plane that cuts through the first octant is creating a line that's y-intercept 2 and the equation 2 minus x. But because you're in the first octant, you know that y has to be bigger than 0, and y has to be bigger than 0, but x also has to be bigger than 0. So here's your region in the xy plane that you're going to integrate over. Okay? So now you can say that the limits, if you want to do this as one of the orders, would be dy dx. Y would go from 0 up to the equation of this line, 2 minus x, and then x would go from 0 up to where that line crosses at x is equal to 2. Okay, so that is one particular setup of the volume integral. Okay, you can try another ordering, right, for the volume integral of 1. And let's say you want to choose dy, d something, d something. Okay. And the trick here is to do like you did before, solve for y. But y would be 6x plus 3y plus 2z equal to 6. Solve for y. 6 minus 2z minus 6x. Y is equal to 2 minus 2/3 z minus 2x. So y would go from, since it's in the first octant, 0, y equals 0, up to 2 minus 2/3 z minus 2x. And notice that your limits are functions of z and x. And now you want to figure out, okay, what happens to this plane when it reaches, when you intersect, what happens when y is equal to 0? So what's going on in the xz plane? But if y is equal to 0, this piece will be 0, and you're left with 6x plus 2z equal to 6. So 2z is equal to 6 minus 6x. Z is equal to 3 minus 3x. So now you found z is a function of x, which is 1, 2, 3, and then the line comes down here, 3 minus 3x. Which means that this will be the region you're going to integrate over is this triangle, but it's in a different plane, it's in the xz plane, which is kind of hard to see, but the algebra will work out. So x, we should do this as a dz dx, because this is the way we solved it. So z can be some function of x. Z would go from 0 up to, you can see right here, z is 0 up to that line, which is z is equal to 3 minus 3x. And x then would go from 0 to x is equal to 1. Okay. Now, if we've done everything correctly, by that I mean setting up your limits of your integrals correctly, these two integrals should give the same answer. So let's double check that now and see how our integrals do. How it's writing assistant. Okay, let's set up an integral. Let's set up a triple integral. Let's set up a triple integral. So 3 single integrals. And then I will do this again. Control C on the next line. And we want to set up these integrals 2 different ways. Number 1, the first integral we can see on the top over here, we set this up as a dz dy dx. And z went from 0 up to 3 minus 3x minus 3 halves times y. And then, let's see, y goes from 0 to 2 minus x. Okay, and x goes from 0 to 2. So that's the first way we set up the problem, where z is the first limit, z is the first integral you set up, and that's usually a common way to see it. But you can also set this up as a dy dz dx. Okay. And so y has to be a function of x and z. The bottom limit was 0, and 2 minus 2/3 times z minus 2 times x. And then z goes from 0, sorry, I'm trying to be real careful here, 3 minus 3 times x, and x goes from 0 to 1. Okay, and let's run these two integrals, and let's see that you will get, okay, 2 minus x. They should give the same answer. I would have to look back at, maybe I made a mistake somewhere. Did x go from, was x from 0 to 1? Nope, I think we had 0 to 2. That's what we thought from the... These two integrals should come out to be the same if you've set up the limits appropriately. So I have to look back at where I made the mistake And it's possible that this could be a parentheses thing. Maybe just put parentheses around our 3/2 so that the y is not treated as being in the denominator. And let's put 2/3 in parentheses. And let's try this one again. 0 and 1. Okay. So we've made, these should give the same answer, so we've made a small mistake, probably, and we will have to find that. I will put the video on pause, and then we will come back and see where we made a mistake. These problems are really involved, so it's not unexpected that a mistake is made. So the resolution to our issue is that when I was doing some algebra, I wrote y is equal to 2 minus x when I think I had 2 minus 2x. So this needed to be a 2x, and when that means that y is equal to 0, like the intersection happens not at x is equal to 2, but when x is equal to 1. And if you put 2 minus 2x and 1 into there, you get 1 for both of the integrals. Okay, so that is the resolution, and I will leave you to set up the other 4 limits, the 4 other iterated triple integrals to compute the volume of the tetrahedron. Okay, you can plot this problem in Mathematica to see like what region you're talking about. Let's take a look at a contour plot 3D. Okay, and we are trying to find the volume of a region. One of the functions is a implicitly defined function in 3 variables, or the 6-level surface of a function of 3 variables, and then put x is equal to 0. Put the equation equal to 6, y is equal to 0. We're plotting all the major planes. Z is equal to 0. And let's plot this from, say, x going from 0 to, say, 2. Y goes from, say, 0 to 2. And the z values go from, say, 0 to 5 or something, just to kind of get an idea. And then contour style. There's going to be a lot of pictures on here, so change the opacity so that you can see through all of them. Okay. And there is the tetrahedron that is being talked about. Okay, you have 2 of the planes. Actually, let's plot this so you can see some of the different octants that are involved here. Okay, let's let z go from, say, -5 to 5. Okay, so here are the 4 of the octants. You can see an octant here, 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 and here. And then there are 4 more in the bottom created by the green and the blue plane. Okay, and the octant we want, the volume is this plane, the yellow plane comes through and slices into this first octant between green, blue, and red, here closest to us in the front. And that region that we are getting, that is what we have found the volume of in this problem. It turns out to be a volume of 1. And so you can see through it right there, the region between those planes. Okay, and inside of that region right there, it's a little triangular region called a tetrahedron. That is the volume we have found to be equal to 1. Okay, and so ends this video.